to get some pre-finish, get a glass of water. It's hot as blazes in here. There's so many flies in the sink. Okay. Hopefully it's not frozen. This is what I was just trying to fix. Okay. Okay. Have an echo now? Shit. Let me see if I can set my speakers up so I can hear it, so I can try to fix that. God damn it. Nothing ever works the way it's supposed to. Okay. Okay. Let's just do that. I can't charge this at the same time. I'm just going to keep going. Let me know if that fixed it or not. Well, let me see if I can hear it. Oh, okay. I think I know what that is. Okay, yeah. Okay, that's fixed now. Okay. All right.
Oh, yeah. Okay, that's fixed.
All right. Okay. Let's stop recording and start it again. Turn this sound off. Okay. So hopefully, yeah, I apologize about that. Sometimes things don't work the way that they're supposed to. So Brian had a question. Is there a reason why I chose to draw the loops on the inner two circuits instead of the larger outer circuit containing both voltage supplies? Or was it a matter of choice? It was just a matter of choice. So I needed to get two more equations out of this. And there were three ways that I could have done this. I could have more than three ways, but there were three loops that I could have drawn. One was here, one was here, and then the last one was out here. You could have done the one on the outside. In fact, you could have done three loops and no junction. Ultimately, there are four different equations that you can get out of this using either a junction or any one of three loops. It ends up just being redundant to do more loops, and it was just a choice that I made. I didn't have to choose this loop. In fact, for this particular problem, it doesn't matter. Sometimes you find that some loops are easier to evaluate the algebra later. This turned out to be pretty easy, I think, regardless of the way that I wanted to define it. But you absolutely could have drawn the loop to go around the outside. That was just the choice that I made. Okay? All right. So that's this one. So let's look at the problems that I gave you guys in class today. So the first one, and like I said, this was, and in retrospect, I realize things as I'm going through and teaching this, and it's not really that this is a hard problem. It's just that it's something that I hadn't really talked about, and that's what makes it hard. Okay, so I think I had a better piece of chalk I left on the floor over here, yeah. Okay, so what this problem says is you have this circuit where you have some switches here. So call this switch 1. So call it switch 1. And then you had some switch 2 here where you had a second capacitor, a resistor. This is V1, this is V2, this is R, this is C1, this is C2, and this is switch switch 2. Okay. So what you're still having trouble determining the sign of the current and the other components, V and C, and equating the currents at the junction. Okay, so Mark, I'll try to come back to that because I erased what I had here, so I can't really talk about that for this particular problem, but I'll try to come back to it for the second set of problems that I have here, and let me know if I answer your question or not. Okay, so for this one, you have this circuit here, and you have these two switches, switch 1 and switch 2. And the way that this works is I'm going to close switch 1 and wait a really long time so that this capacitor is fully charged. And then what I'm going to do is I'm going to open this switch and close this switch. And what I want to do is I want to find what the current is through this resistor and what the charge after I do that operation is going to be on the capacitor C1 and the capacitor C2. Okay? So when I close this switch and this switch is open, what's going to happen? Well, I can draw some loop to go around here, and I can label some charge plus Q1 and some minus Q1 here. And going around this loop, this is probably the simplest loop that we can think of. It only has two components in it. So call this loop 1. So the integral around loop 1 of E dot dl is going to be equal to minus V1 plus Q1 divided by C1. And this is equal to 0. Okay? So what we can say in this first state, I'm running out of labels here. Let's call this state A with a circle. Okay? So state A with a circle is just the first state where I close this switch and I have this one open. So for state A, what this says is the charge on this capacitor C1 can be found from this equation that I got from this loop. And that says that Q1 is just going to be equal to V1 times C1. Okay? Now let's look at the second state that we have, and I'm going to label this as state B. So state B, I'll redraw the circuit. So I'm opening switch 1. And now I'm closing switch 2. So this is R, this is C1, this is C2.